Okay, good morning. So today we're continuing with the idea of momentum, and what we're going to be examining today is the idea of angular momentum. And this is not too long, so the way I've got it sorted out, and so I'll say a little bit about the test towards the end of the lecture, since that's probably okay. So I'm just wanting to check a few things here, because this really isn't working, is it? Yeah, there it goes. I think the last week I was having trouble with some of the live streamed recordings. We're not capturing the other screen. They seem to be capturing it at the moment. Right. So what we're going to talk about today initially is the idea of the moment of inertia. And this is something that's analogous to, in what we've been discussing earlier, it's analogous to the mass. So if you have something with a large moment of inertia, it's difficult to turn it. So if you've got something, a big heavy wheel, it's hard to turn. If it's a small light wheel, it's easy to turn, just as a small weight is easy to accelerate and a large weight is difficult to accelerate. So the moment of inertia has this definition. Now we're really, in this lecture, we're actually just defining a lot of things without deriving them. If we wanted to derive these things properly, we'd need another lecture or two, which is why we've left them out at the moment in the course. But this is an important concept, moment of inertia. I is m1r1 squared plus m2r2 squared plus m3r3 squared, etc. So if you have some sort of object rotating about some axis, it has m1, m2, m3, r1, r2, r3. Seems logical that the increasing the mass would increase the moment of inertia, and that increasing the radius would increase the moment of inertia. But just as we found when we were talking about acceleration and circular motion, the acceleration in the circular motion was proportional to the velocity squared. So in an analogous way, the moment of inertia is proportional to the radius squared, not just the radius. Now, one of the things that I think has been really sad lately is that these roundabouts that we used to have in children's playgrounds, I think they've decided they're a little bit dangerous, and you see less of those, because those roundabouts are really great physics tool. You can, if you can find a roundabout, one of these old-fashioned roundabouts, do go and play on it a bit, and you can really see the difference between having people sitting out on the edge of the roundabout, sitting in the middle of the roundabout. It's much more difficult to turn the roundabout if the other people are on the outside. Okay. Now this slide has a lot of definitions which we're not going to use, and in fact we haven't actually defined them very well here, but I want to mention them because these are, most of you are going to want to go on to PHYS 101 next semester, and in PHYS 101 you're going to do a lot about rotational motion, and you're going to be using these ideas a lot. So we've so far talked about force, mass, acceleration, and often the net force, and the acceleration was the net force divided by the mass. So since the test today is using all these concepts, hopefully you're reasonably familiar with those. Now, in terms of rotations, there are some new concepts. There's the torque, and I don't think I even defined that on the slide, but the torque is the distance from the center of rotation times the force, so the perpendicular force. So the torque, if you're rotating about here, it's this force that's perpendicular to that radius multiplied by the radius. We're not actually going to use that, but it's a bit confusing if you haven't actually heard the definition. And then the moment of inertia, this is this mr squared thing. And then there's an angular acceleration. And back in this lecture, everybody cares a lot about security these days. The lecture a week ago, we were talking about circular motion, and we talked about the angular position, which we measured in radians. And I'll come back to that again, but and then we talked about the where's it gone? We had omega, the rate of change, d theta by dt. So that was the angular velocity, the rate of change of the angle, and then the angular acceleration, just like the regular acceleration is the change of velocity in per unit time, the angular acceleration is the change of is the change in angular velocity per unit time. So again, we're not going to use that. When you get to PHYS 101, you're going to be using that all the time in the mechanics section. And so similarly, there's an expression, the angular acceleration is the torque divided by the moment of inertia. So as it says at the bottom, we won't use angular acceleration or torque in this course, but it's useful to have an idea of what it's about. So what we'll do is talk about the moment of inertia, because then we can talk about conservation of angular momentum, and that's an interesting thing to be talking about. So here's a little example which is maybe a little bit hard to follow on the thing. What it's saying here is that if we have a mass m1, m2, m3, and suppose we rotate we rotate about this axis. So we're rotating about that axis, so M1 isn't actually doing anything, it's just sort of rotating. M2 and M3 are some distance from the axis. This is 10 centimetres or 0.1 metres. And so if we want to work out the moment of inertia, I is M1R1 squared plus M2R2 squared plus M3R3 squared, and the masses were 1 kilogram, 1.5 kg, 1 kg. All we have to do is add this up, and of course the M1 is the distance of M1 from the axis of rotation is 0, so we don't need that. We just need to add up the other two. Now, on the other hand, we could reframe it. We could take our same three masses, M1, M2, M3, and we could rotate them in an axis that's coming out of the page. So we can rotate about this axis. And now R2 is still 0.1 metres, but the distance from the axis here is going to be 0.1 times the square root of 2, right? If these were 1 and 1, by Pythagoras' theorem, that would be the square root of 2. So that's 0.14 something, 141 metres. So the moment of inertia of an object depends on what axis you rotate it about. So, you know, if you have something like this pen, rotating it about an axis that goes through it's perpendicular to the middle of the pen, is more difficult than rotating it about an axis that goes along the axis of the axis of where the pen is, right? So that should be fairly familiar. So this is just an example of that. Okay, so for the first case, we're just multiplying 0.1 metre by 0.1 metre, we have to square it. So it's 0.01 times 1.5 gives 0.015 kilograms metres squared for the second mass. And the third mass was only 1 kilogram, so it's 0.1 squared times 1, 0.01. The first mass, the R was 0, so there's no contribution. 0 squared times 1 is 0. So the total moment of inertia is 0.025 kilograms times metres squared. Whereas when we do the rotation about this axis, now this distance R3 is bigger, so the value here turns out to be bigger, and the moment of inertia is a little bit bigger. So that's not a terribly difficult calculation, but I just wanted to go through it reasonably slowly because this is a new concept, probably, if you've not really done much of this before. Now we wrote that, we've said that the moment of inertia, we've initially wrote it in terms of separate masses, but we could write it as a sum over all the masses of mi times ri squared. And then if we have something which isn't just individual masses, something which is, say, a disk or something, then we have to sum over all of those. We have to do a sum over all of the little bits of the disk. So the bits out at some little bit out at the edge will be the moment of inertia contribution of that will be the mass times r squared. The ones closer in, it will be smaller. And if you actually go through that calculation, which we're definitely not going to do here, you get a half, because the ones out at the edge contribute mr squared. If you're in the centre, it contributes nothing, and when you work it all out, it turns out to be a half. So these different shapes have these different moments of inertia, and you can work this out using calculus, using integral calculus. But that's a little bit beyond what I want to do in this course. The main point to take away from here is that if you have some object, it's possible to work out the moment of inertia about a particular axis. So you can see here we've got this slab here where the axis is around through the centre, 12th ma squared. Here it's at the edge. It's bigger, a third ma squared. So that's analogous to the way the moment of inertia about this axis was different from the moment of inertia about this axis. So it's just a more complicated version of that. Right, so that's moments of inertia. And now what we want to do, now that we've got this idea of moment of inertia being similar to mass, back to that. Got a moment of inertia which is analogous to mass. We've got a velocity we've got an angular velocity which is analogous to regular velocity, and now we can define an angular momentum, L equals I omega. Momentum L equals I omega, whereas before we had P equals m times v for linear momentum. Now we have angular momentum, L equals I omega. And let me go back to the other lecture. So remember what we did a week ago. We talked about omega. That was the angular displacement delta theta over the time interval delta t. And a really key concept, which I think I did this quite at the end of the lecture, so I probably rushed through it a little bit too much. The theta here is measured in radians. What does that mean? Well, if we have an angle theta, if we've done a rotation, our rod has a certain radius. We have S. Theta is S divided by R. It's the arc length divided by the radius. And so if we go around a full circle, that's R. The arc length around a full circle is what? 2 times pi. 2 times pi times r. So theta full circle is 2 pi r, the arc length, divided by the radius r, which is 2 times pi, which is what, about 6.28. Whereas in radians, in degrees, you go around a full circle, that's 360 degrees. Now the reason why we use radians rather than degrees is that degrees are a purely conventional kind of idea. I mean, they're a very useful idea. We use degrees because they have lots of factors. So a quarter of a turn is 90 degrees. You know, an eighth of a turn is 45 degrees. It's the same reason why we use a dozen. You know, we have a dozen eggs rather than 10 eggs or something. So that's useful. But when we start doing these calculations, if we were using degrees, we'd have to put in a whole lot of factors of 360 divided by 2 pi, and it would get really, really annoying. So we don't do that. We measure our angles in radians. So we can go back to angular momentum then, and so since I was the sum of all the masses mi ri squared, and omega was d theta by dt. Oh, sorry. Thanks. Need a bigger page, don't I? Okay, since we're doing that, then the moment of inertia is kilograms meters squared. The omega, the angle. Although I've written down radians here, this angle doesn't really have a unit in the sense of having a unit like meters or kilograms or time, because that angle was just the way we're measuring the angle. Theta is s over r. Those are meters over meters. There's actually no units there. So this is so the units of this are just 1 over seconds. So the SI unit of angular momentum is the kilograms meters squared from the moment of inertia, and then divided by seconds for the 1 over time in that expression there. So that's repeating what we were saying. We've got torque, the twisting force, moment of inertia, angular velocity, angular momentum, and these are analogous to the linear terms, the linear dynamics terms. Now the thing we want to do now is to talk about conservation. Remember, that's what we did in the last 2 lectures. We used momentum conservation to do calculations. So we were saying that the final momentum was equal to the initial momentum. So we had some situation, maybe our balls flying together and maybe sticking together. Now that it's going a bit faster or something, or that's a bit bigger. So by using using the idea of momentum, we were writing, we were saying the initial momentum is equal to the, let's write the other way around. The initial momentum is equal to the final momentum, and since we had formulas for working out what that initial momentum was, what the final momentum was, we did several problems last week solving for, how fast these balls collide, how fast do they go after they've collided. That was a very powerful way of solving those problems. So we can do the same thing with angular momentum, and obviously the simplest thing is that if there's no torque, analogous to having no force, then if we have something that's rotating, if there's no torque, no frictional force to slow it down, it's just going to keep rotating at the same angular speed. Just as if in the momentum case, if we have a particle that's just moving, it's just going to keep moving. The angular momentum is going to be conserved. What's going to be more interesting is that if the moment of inertia changes from the initial, between the initial and the final situation. And an example of that is example of someone like an ice skater or a skier or something. If you watched the Olympics a few weeks ago, them rotating, and you'll notice that when people do some of these tricks on trampolines, skis, whatever, or ballet dancers, they'll vary their moment of inertia often by changing where their arms and legs are. So they can change their moment of inertia. Their angular momentum is constant, and so the speed at which they're rotating changes. In fact, with these aerial things, you can do more complicated things where you're not only changing you can even change the axis you're rotating about, but that's more complicated than what we're considering. We're going to consider just this very simple rotation. So let me try, see if I can make this work. Let me just check that it does change over. Okay. So we have a nice demonstration of this, and you'll be able to. The gear is actually outside, is on the third floor of the Ernest Rutherford building, but it's very difficult to bring it over here. So I've brought a video. It's one of our students last year. So in this video, we're going to rotate him and get him to change his moment of inertia. He's rotating, he sticks his arms out, and he's going to slow down considerably. I've got the sound off, but he started, if you listen to it, he's complaining that those weights are very heavy and it's hard to hold them up. So in the second part, we started off with him with his arms out, and when he pulled his arms in, you could see he speeded up, and when he puts his arms back out, he slows down again. So this, as I said, this chair's up on should be up on the third floor of the Ernest Rutherford building. If you want to go and have a play with that, I'd encourage that, because it's always good to actually go and see what these things feel like, not just not just see what things are like as formulas on a page. Okay. So this little problem here is pretty much exactly the same as what you saw with the student in the chair. So here we've got the rotation. Write this down. So we've got the initial, the before. Fi is 2 revolutions per second, and there's 2 masses. The radius 0.7 meters, and the masses were 5 kilograms. 5 kilograms. So that's before, and then after. The masses are in closer, 0.25 meters, but the same masses, 5 kg. 5 kg. So then what's the final rotation frequency? So that seems like a reasonable thing to be trying to calculate. So initially we have I, moment of inertia initial, omega I, and we have moment of inertial final, omega F. And so what's the initial moment of inertia? Well, there's a 2 because there are 2 masses. And then it's m is 5 kilograms times Ri squared, or 2 times 5 times 0.7 squared. Final moment of inertia was 2mRf squared, which is 2 times 5 times 0.25 squared. So that part of it's easier. What about the omegas? Well, the omega is our angular frequency, or angular speed. Omega is 2 times pi times the frequency. So it's sort of how many radians per second. So if you go around once in a second, you're going around 2 pi radians. So omega is 2 pi times f. Now, when I wrote this down here, I've already written in the mass. But I think you can see that if we can cancel the mass out when we do this calculation. So if we say if omega f equals I omega I, so this is 2mRi squared times omega I, or 2 pi Fi, and this is 2mRf squared omega F. Sorry, I shouldn't put a square there. That was our moment of inertia times omega. That omega F is 2 pi final frequency. So instead of instead of putting in all these numbers, we can just cancel them out, because the 2m cancels on both sides, the 2 pi cancels on both sides. So we can write f final, that's what we want to solve for, is equal to f initial, and then it's Ri squared divided by Rf. Rf squared, which with a bit of luck will be the same as what we have over here. Okay, so that's so we can solve for the final frequency. Whoops. And if we put the numbers in, the initial frequency was 2 revolutions per second, I believe. Yeah, 2 revolutions per second. So we put that in. The final frequency is, turn that off. Damn it. Go away. The final frequency is quite a lot more than that, and you could see that from the example of the student on the chair. When he pulled in his arms, he went considerably faster. I don't want to go through that one. That's just complicated. Okay. So we've got. So this is the conclusion of this little section. We talked about the moment of inertia and the angular momentum, and we used conservation of angular momentum to do some calculations which are actually quite relevant in certain circumstances. You know, if you're a ballet dancer or something. So far we've been talking about conservation laws in terms of momentum, and we've done linear momentum and angular momentum and solved these problems in various ways with forces and so on. And what we're going to do next time is to go on to energy. So momentum is one of the key conservation laws in mechanics, and energy is a key conservation law in all of physics. You know, so that's a really important thing to know about. So the last two mechanics lectures are going to be about conservation of energy. Okay, so before we stop here, let's go back to the course. So we're going to be, as you know, we have a test today. That's at 7. We have a drop-in session at 5 o'clock, and I'm going to go home, so I can run the test from home, but I'll be available on Zoom at 5 o'clock using this Zoom link. And there's a whole lot of information about tests and exams down here. And I've already had several students. I know we're in a really difficult time with COVID. I've had several students email me and saying they've just had a COVID test and they're feeling really bad, and they're not going to be able to do the test today. And people with other circumstances. So if you have if something develops today like that for you, send me an email, and I will arrange for you to be able to sit an alternative test later in the, either late this week or early next week, just depending on how people's schedules work out. And the other alternative is, and this is general for any of these large items of assessment, anything that's worth 10% or more, if you miss it completely, you can apply for a special consideration. So if you're sick, you had a death of a close friend or relative, other things like that. There's an official application, so that's always an option. I mean, I'd encourage you, if you can, to sit a make-up test, because it's better for you to actually do the test and see how you're going. So as far as the test is concerned, I've put up a formula sheet here, which is the formulas that we've been using in the mechanics course. This is only weeks 1 to 3, so it doesn't include conservation of momentum and so on. So I'd encourage you to have either have that there or have something similar for reference. There are some sample tests here where these are tests, a couple of the tests from the last 2 years. And what I've done here is give you references to where to find out how to do those questions. So I haven't given you the answers, I've given you the references to, you know, this is a question from Lecture 5, example 3.14 or something. Because I've found, and several students last year commented this was really useful because it forced them to go and actually look at what was in the derivations of those examples. I realise though that you also want to be able to do things where you get feedback about whether you got them right, and these revision exercises. These give you some examples where you can get instant feedback. So you can choose something. I've already done that one. And I got the wrong answer because I just guessed, but this is a typical sort of question, right? The pushing blocks and working out forces. And you can do these questions and get instant feedback on them. So there's each time you do one of those revision exercises, you get 10 questions, and they're randomly selected from a database of maybe 50 questions. So you'll get quite a lot of different questions. Do be aware though that there will be some of those questions will be quite difficult. So if the questions look really, really difficult, compare them to the questions that we've asked in the tests in the past 2 years. And if they're obviously way more difficult than that, don't worry too much about them. So here you should be able to see all this stuff. The test, there's a student agreement. You're agreeing that this will be your own work. It's an open book test, but you shouldn't be talking to other people, and you shouldn't be posting the questions on some internet site asking what the answers are. So you have to read that and say, I've read the message, and then you'll be able to. It's quite annoying. You have to then go back. So do that as soon as possible. Then you'll be able to access the test. So the test will come up, and it'll say when you can access it. And for those people who are overseas, hopefully this will come up with the right time in their time zone. And the test is it's normally a 1 hour test, but I've given you an extra 10 minutes because you're expected. In one of the questions, you'll have to draw a diagram, write some things down, and take a photograph and upload it. And that shouldn't take more than 10 minutes, I hope. So the test starts at 7. Once you start, you'll have 1 hour and 10 minutes. except that it will close at 8:30. So you really want to start, by about 7:15. Now, if you have some problem, if your internet goes down, you have a power cut, don't worry too much. The test will keep whatever you've done up till now. And, so if you just get cut off for a few seconds, it shouldn't matter. It will remember any questions that you've already answered. If you have a serious problem, email me or phone me. There's a phone number there. It's my office phone number, and it'll ring on my mobile phone. And it's best to tell me as soon as possible, because it's quite easy if you call me up and say, my internet's been out for 15 minutes, it's very easy for me to extend your time. If the test is already finished, it's a little bit more difficult. I have to do a bit more fiddling with the system to get that to work for you. So if you have a problem, tell me as soon as possible. Right. So I think that's all I want to say. I don't know if there's anybody here have any questions or. No. Yes? Yeah, each test is worth 10%.
How much is the final question worth?
Final, right?
So I understand that the test was like 10%, so how much was the final question?
I think all the test out of 60 and the multiple choice questions out of 5, out of 5, and this one, and maybe written one out of 10. Yeah, it's good.
Sometimes you have to replace the screen because it's late.
Oh, it takes a while, yeah. Well, I think it takes a while to do the obviously the.
Change the slide.
Yeah, yeah.
Otherwise, when you are writing and you are moving the pen, right?
Yeah.
But when you switch the slide, then
It takes a little.
yeah,
There's a lag in the. There's a noticeable time lag here in the streaming anyway. I mean, that's just a time lag. I mean, you haven't.
But they will watch like later, then it will be right.
Oh yeah. But they should be getting this. There's a time lag in their sound as well, so it's. I think, isn't there? How are you getting on anyway? Yeah. How's your calculation?
I am doing today.
You'll do today?
Yeah.
Ooh. Are you sure?
First, I will try to find out the distance that you told me. Right?
Oh, that's right. Yeah. Yeah, I mean, that shouldn't be. It's not too difficult. It's just a little bit. It's just a little bit tedious, right? But in the case of. In that particular case, it's not actually that.
that.